Hello and welcome back to the discussion sessions of production technology course theory and practice. Now, let me remind you that last time what we discussed are the tool angles. So, we said that we have three sets of angles, one set of rake angles, one set of flank angles and one set of cutting edge angles apart from the tool nose radius. So, we have altogether 7 parameters, 2 rake angles, 2 flank angles, 2 side cutting edge angles and the nose radius, by which a tool in any system is nomenclatured. And then we have seen that there are different systems depending on the country which is adopting that. The systems are coordinate system, orthogonal rake system, normal rake system and so on. It was also said that normal rake system is the one which is the international system, and most of the countries are now trying to adopt that system, so that everywhere the same standard is used. Afterwards, we said that however, right now we have different systems. So, if we are purchasing tool from one system, it has to be actually the angles have to be converted to another system, and I have shown it to you that conversion of the angles is not so difficult, because all the views could be taken in one place and they can be correlated. Then geometrically you can find out the relationship between the angles of one system and the another system. Then we started discussing the selection of tool angles. So, let us see in this slide. With 0 inclination or back rake angle, we said that the chip will flow parallel to the workpiece surface and it may cause a removal problem. Okay. So, we have to have some sort of inclination angle and some back rake angle. Okay. Now, with appropriate inclination or back rake angle, the chip can be made to flow away from the workpiece and strike a suitable chip breaker, curl and break into small fragments. Okay. So, I talked to you about the chip breaker. Continuous chip is not desirable all the time, because it actually rubs, entangles and so on. So, therefore, we have to have some sort of provision, some kind of a provision to break the chip. Okay. Now, these provisions are the chip breakers, and chip breakers are of different types. Chip breaker can be a protrusion on the rake face, an indentation or the crater on the rake face. Okay. Now, sometimes the research went on for imparting some sort of small amplitude vibration to the tool, so that with that vibration the tool can vibrate and break the chip. However, that research did not go well, because along with that vibration which is imparted to the tool, and the tool imparts in its turn to the workpiece, the marks will be, feed marks will be there, vibration marks will be there on the workpiece surface. So, that actually spoils the surface finish. So, therefore, that research really did not go well. Okay. Now, the side rake, orthogonal rake and normal rake, that is alpha S, alpha 0, alpha n. If you remember that side rake was in the ASA system, orthogonal rake was in the coordinate in the ORS system, orthogonal rake system, and the normal rake was in the normal rake system, that is the international system. These angles particularly influence the cutting forces, power and surface finish. Okay. The larger is the rake angle, the lower are the cutting forces and power, and better is the surface. Well, precisely what we say is that I showed it to you yesterday, last time probably, that if it is the cutting force, for example, and if it is the alpha which is one of them, so it goes like this, meaning that as the alpha increases, so the FC actually decreases. Okay. So, we always want the cutting force to be decreased, because the power, let us say power P, this is equal to FC and the Vc. So, Fc if we can reduce, Vc being constant, in that case the power is reduced. Okay. So, this is what is our aim, that to reduce the power Fc and the power as much as possible. Okay. So, that the less power is consumed for the process, and the process could be cheaper that way, because last time I have actually discussed that once the power consumed is less, in that case the prime mover of the machine could be less powerful, that is cheaper. Okay. And finally, the product that you are making out of that machine will be cheaper, and you can compete in the market with that cheaper product. That is the idea actually. So, here one of these, that is the side rake angle, orthogonal rake angle, or the normal rake angle, if one of these rake angles is increased, then the cutting force is decreased. Okay. Why it happens? It is actually the physics behind this can be explained in the following way. Suppose we have the cutting process viewed, I am just exaggerating that because otherwise it will be difficult to explain. Let us say this is the workpiece. Okay, this is the workpiece, this is the chip flowing. All right, let us say chip velocity is this. All right, and of course, this is the tool. Okay, this is the tool, and here we have the certain rake angle, okay, alpha, one of these rake angles, alpha s, alpha 0 or alpha n. So, this is the cutting velocity V c, and this line is the perpendicular to the cutting velocity vector, that is what we said. Okay. So, now what we are saying is that this rake angle, if it is increased, then the cutting force will decrease. So, the physics behind this is that suppose you are increasing the rake angle, okay, increasing the rake angle, and the tool becomes like this. Okay. So, now the angle is alpha 1, and the alpha 1 is more than alpha initially. Then what happens is, with the chip as it was flowing with the alpha, this will now flow like this. I will give it in dotted line, okay, something like this. All right, something like this. So, this is the new position of the chip, and the chip will be flowing along this rake face. All right. Now, from this point, tool point, to the point where the plastic deformation starts, this is called the shear plane. Okay. And this angle that it makes with the direction of the cutting velocity vector, this is the shear plane angle. All right. Now, with the shear plane, as the alpha is increased, it becomes from here to this way. This is the new shear plane. Okay. So, as you can see, the length of the shear plane is decreased as the angle is increased, rake angle is increased. As a result, what happens is that less effort is required to remove that area, and the less force is required. So, only because of that the length of the shear plane is decreased. All right. Now, it is the phi 2, and as you can see that the phi 2 is more than phi 1, let us say phi here, okay, because of the alpha increasing, because alpha goes from alpha rake angle goes from alpha to alpha 1. So, therefore, the length of the shear plane is decreased, area is decreased, and the less effort is required. So, the force is decreasing, and if the Fc is decreasing, I showed that the power consumption will be less in the cutting process. So, the surface finish will be better, because the force, when the cutting force less, then the power, the surface finish also improves. Okay. The surface roughness becomes less. So, these are the reasons when we can actually that we can consider to control the process, okay, so that the force could be less. Now, if you see in this diagram, all right, that when we are increasing the rake angle, for example, from alpha here to alpha 1, in that case the tool becomes from with a hashed one. The one which is hashed is the new position of the tool or new shape of the tool, where if you see the tool is weaker, all right. The material here in the tool will be less as we are increasing the alpha. Okay. So, this is what it is written, that the large rake angle, however, decreases the cutting angle. So, cutting angle is actually this angle. Okay. This is the cutting angle. Okay. Now, this cutting angle is between the rake face and the flank face. This cutting angle actually decreases as we are increasing the alpha, that is the rake angle, and the tool is becoming weaker because the tool is becoming thinner, okay, and the less material is available, and less material is available means that material will not be sufficiently conduct the heat, because more material, when there is more material, the heat conduction is more. Okay. So, less material will be available to conduct the heat. That is why it is written here that large rake angles, however, decreases the cutting angle between the rake and the principal flank faces, and less metal is available to support the tool. That is the less strength of the tool, because tool is becoming then weaker. Okay. Tool may not be able to withstand that much force as in case of the earlier tool when the rake angle was less. All right. Less strength of the tool and conduct the heat generated due to plastic deformation and the friction. Okay. The heat that is generated because of the plastic deformation and because of the friction between the chip and the rake face of the tool, that heat will not be conducted as much as it used to be for the lower value of the rake angle. Rake angles, therefore, we cannot really infinitely increase the rake angle to get the benefit of reduced cutting force or reduced cutting power, all right, because there is a constraint that if we increase more than a certain value, let us say, in that case the tool will be weaker and the less heat will be conducted. What does it mean less heat will be conducted? Is that the heat will be accumulated in the tool and the tool will have the thermal deformation. Okay. As a result, the tool geometry may be lost, rake angle may be lost, flank angle may be lost, and overall the tool may be thermally deformed, all right, and the tool life will be less overall. So, because of those constraints that with increase in the alpha, that is the rake angle, we cannot infinitely increase it, all right. Now, the rake angles may be positive or negative depending upon the desired tool strength, all right. For rough machining, often carbide tools with negative rakes are used. So, when we discussed the carbides in the material, I told you that that material is used for making the tool, but those carbides are very brittle. Okay. So, carbide tools with negative rake angle, when it is used, then the tool becomes fatter. So, what is said here, that the tool may be like this. Let us say this is a turning tool, it may be like this, it may be like this, I mean to say the shape of the tool, okay, or it may be like this, all right. So, in all this I am just showing the rake angle, because you understand that in all this is the flank angle, okay, but this is the rake angle, all right. Here this is the rake angle, here this is the rake angle, okay. So, as you can see, the rake angle can be that alpha is equal to 0, here the alpha is positive, this is called the positive rake angle when it is in this way, and when it is in the opposite direction, this is the negative, okay, with the negative rake angle. So, therefore, it is said that with a 0 or with a negative rake angle, you can actually use when we have the tool strength required will be more, because as you understand that if it is 0, or if it is negative, then the tool here, tool material available will be more, all right, and tool is fatter than in case of the tool with the positive rake angle. Okay, with positive rake angle, the tool strength is less than in case of tool with a 0 rake angle or with a negative rake angle. All right. So, when we use let us say the ceramic tools, as the ceramic tools are brittle, it cannot withstand the shock, okay, or any kind of fluctuation in the force. So, in that case the tool has to be has to have more strength. To have the more strength, we need to have the tool fatter. Okay. So, in that case either 0 degree of the rake angle or negative rake angle can be used to strengthen the tool and to have the less thermal deformation, because more material will be available to conduct the heat from the tool. Often carbide tools with negative rakes are used, that is what I said. Now, side rake, orthogonal rake and the normal rake usually vary between 5 and 10 degrees, 5 and 15 degrees, okay, for a single point HSS tool. Now, of course, this range is quite a wide range, like 5 to 15. So, now it depends on the work material. For example, if the work material is hard, okay, then of course, you need more force and the tool has to be stronger. In that case, you understand the rake angle has to be less, okay. And if the tool vice versa, if the workpiece is softer, then you need more, you can get more the rake angle. In that case, the tool does not have to be that much strong as in case of the hard workpiece material. And in case of suppose your tool is weaker, tool is of a material which is weaker material, the strength of the material is not very high. In that case, you need to have the rake angle which is low, because in that case the tool has to be fatter, tool strength has to be more, and so on. So, this is the judgment of a good engineer, okay, to select the right kind of the rake angle depending on the material combination given, depending on the situation, that means that depending on the work environment, depending on the cutting parameters and so on. So, overall we said that the range is between 5 and 15 degree. However, we can have the rake angle as 0 degree, as negative rake angle and so on. Okay. Higher values are used for softer work material, as I said, like aluminum. In general, harder is the work material, lower is the rake angle. That is the thumb rule, that harder is the work material, obviously that, as I said, that the tool has to be stronger and the rake angle is smaller. Okay. For example, the recommendation for steel, the alpha S, alpha 0, alpha n, these values lie between 8 and 12 degrees. Okay. But for cast iron, these values are 5 to 10 degrees. As you can see that these values are less than the values in case of steel, because the cast iron being the brittle material, it is a very strong material as well, I mean hard material as well. So, for hard material like cast iron, the tool has to be stronger and the rake angle therefore chosen or range chosen is smaller. Okay. Now, as far as the flank angles are concerned, flank angles minimizes the rubbing of the flank faces with the machined surface. Okay. So, what is meant here is this, I will again draw this picture. Let us say I am not drawing fully the workpiece, this is the tool, all right. So, this is the flank angle, I will once again point it out, that this is the flank angle, okay. This is the workpiece, okay. This is the chip flowing, this being the tool. So, what happens is that this is already work material or already work surface, okay. This has already been made. So, when the tool actually removes chip material, then the flank face rubs against the already machined surface, all right. So, therefore, we have to have the flank angle to clear the flank face from being rubbed over the already machined surface. So, therefore, the flank angle is also called the clearance angle, because we need to clear the flank face from the already machined surface. Okay. Now, higher values of flank angle will reduce rubbing, but also weaken the tool, because if the flank angle is increasing, in that case the cutting angle, this angle is decreasing and the tool is becoming weaker, less material will be available to conduct the heat, there will be thermal deformation. So, therefore, we cannot really infinitely again increase the flank angle like in case of the rake angle that we have discussed, okay, because it will weaken the tool and it will have the less material for the conduct of the heat. Flank angles fortunately have no influence on the cutting forces and power like in case of the rake angle. Okay. So, angles large enough to avoid rubbing is generally chosen, because we are safe. If it is small, if it is bigger, in that case, I mean the larger value, in that case it will never rub off the work surface. So, we are safer, all right, but it should not actually affect the tool strength, that we have to see, that we should increase into that extent, increase the value of the flank angle to that extent, so that the tool strength is sufficient for that particular process, that is the thumb rule. Okay. And here also the angle range is about 5 to 12 degrees for HSS, higher for softer and lower for brittle material. Okay. Meaning that if we have the softer workpiece material, okay, workpiece material is soft, in that case it can be higher, because in that case tool strength is not required to be very high, like I already discussed in case of the exactly the case of the rake angle, all right, and vice versa, that is it can be lower, this value can be lower if the workpiece material is hard or the brittle material like the cast iron, for example. Now, the cutting edge angles provided to clear the cutting edge from the machined surface. I would like to remind you that the cutting edge angles are like this, that if this is the tool in that case, and this is the principal cutting edge, okay, principal cutting edge, and this is the auxiliary cutting edge. Okay. Auxiliary cutting edge. Now, with respect to the x axis, all right, if this is the system of axis, let us say this is x and this is y, this angle in the ORS and NRS, okay, this is given as the cutting edge angle, this is the one cutting edge angle and this is the another cutting edge angle. So, probably this was principal cutting edge angle and this was end cutting edge angle. No, this is the end cutting edge angle in one of these systems. So, you can find out anyway. One of what I mean to say is that principal cutting edge and auxiliary cutting edge of the tool make angles of cutting edge angles with respect to the x axis, all right. Of course, you understand that in case of the ASA system, this was the angle given, all right, and that was probably side cutting edge angle, and so therefore, we said that the side cutting edge angle is 90 minus this principal cutting edge angle. So, these angles are provided to clear the cutting edges, principal cutting edge and the auxiliary cutting edge from the machined surface. This is to reduce the tool chatter as well, affects the tool life as well as the surface finish. What we mean here to reduce the tool chatter means that when this angle is changed, okay, not the correct angle is given, gamma p and gamma e, they are suppose small, and it is not able to clear sufficiently the cutting edges from the machined surface, let us say. So, in that case what happens, the forces, components of the forces which actually try to detract the tool from the workpiece, okay, let us say this is the turning process going on, and this is how the tool is located. This is the workpiece. So, now this is the radial force or the components of the radial force which will try to retract the tool from the workpiece, all right. These forces increase. Now, once come back to the contact point, okay, again it will try to retract because the cutting edge angles are not appropriate. So, therefore, what happens is there will be a vibration, okay, and that vibration is the self excited vibration. So, this is therefore, it is called the chatter. Chatter is the self excited vibration where the source of energy comes from within the system, not from outside, you understand that, okay, because outside when the source of source is from the outside, it is a forced vibration and so on, okay. So, anyway, that is to reduce the tool chatter, we have to have the appropriate value of the principal cutting edge and the E n gamma p, okay, because this also will affect the surface finish. So, the source of vibration, when it is once again it is from within the system, it is the tool chatter. So, to reduce the tool chatter, we have to have the appropriate values of this. Now, as I was explaining that these components, when they actually increase, so the tool starts chattering. This will also affect the tool life as well as the surface finish, because as the tool is chattering, as you understand that the tool life is less, okay, and the because of the tool chattering, there will be marks on the feed marks, we say that on the workpiece. So, the workpiece surface finish will be spoiled, all right. Now, the nose radius, about the nose radius, I actually told you that nose radius is given because sharp tool will always have a very high stress concentration, all right. If it is a sharp tool, there is a very high stress concentration around this point. So, therefore, the tool actually is given a kind of a tool nose radius, and that tool nose radius decreases the stress concentration around it, and also it improves the surface finish. So, I told you in the last discussion session that the surface finish, when we will discuss the chapter surface finish, then I will tell you how the surface finish improves when the tool nose radius is given. Now, here improves the tool life and the surface finish, okay. Large nose radius, however, suppose if it is not appropriate, all right, in that case increases cutting forces and power, because as you understand that it will have more area for cutting, and therefore, the cutting forces and the power will be more, and this causes chatter. So, this chattering is also the same principle, that those radial component of the radial forces which will retract the tool, it will actually increase because of the high nose radius, and it will actually again start chattering, all right. So, that is the self excited vibration, and the tool life will be less, surface finish of the workpiece will be bad, and so on. Normal recommended values are between 1 to 3 millimeter, okay, of the nose radius. So, below that, of course, you will have more stress concentration, and the higher than 3 millimeter, it will have the chattering more, and the tool life will be less, okay. Now, this here is turning operation is shown. This is the 3-jaw chuck, this is the workpiece mounted on the 3-jaw chuck. We will demonstrate this principle of the working in the laboratory when we will go to the lab. I will show you in the lab. Then here, as you see that the workpiece initial diameter is d0, and the diameter that we are getting is the df, okay. So, therefore, the depth of cut is this value, is the depth of cut, that is this diameter minus this diameter divided by 2, okay. This is the feed direction, this is the tool, this is how the chip is being formed, and the chip is flowing on the rake face of the tool. This is the 3-jaw chuck. Here is the rotation is given to the workpiece, okay. So, the forces which act on the tool during the cutting process are shown here. So, this is the force which is in the feed direction, okay. This is the force which is in the radial direction, and this direction is a cutting force acts which is in the vertical direction as the cutting process goes on. Here it is written, schematic illustration shows that a turning operation showing depth of cut, okay. Feed is the direction here, cutting speed is the surface speed of the workpiece, okay. This is given by rotating the workpiece here. Fc is the cutting force, as I said that this goes in like this, all right. Ft is the thrust force, this is the thrust force. So, I will explain it to you a little later what is thrust force, okay. Fr is the radial force, I told you about that this is directed in this that tends to push the tool away from the workpiece being machined. So, if you remember I told you that if the radial force is increasing, so this will actually chatter, okay, and this chattering comes particularly when we have the larger than required nose radius, for example, okay. Now, if you see, let me explain it here. The forces, if we want to couple those forces, let us say this is the tool tip, okay. First I will write a parallelepiped, okay, like this. This is the parallelepiped, okay, and let us say here we have the tool tip, okay. This is the tool tip, this position. So, here this is the feed force Ff, this is in the direction of the feed motion, the tool is moving like this. This is in the radial direction. So, this is the Fr, radial direction. The summing of that will be the Ft, okay, thrust force, all right, and the cutting force will be in this direction here. You see, this is the one, this is the cutting force Fc, okay, and the resultant force will be from this to this point. If you connect these 2 points, this will be the resultant force. So, therefore, this is the tool tip, mind it, okay, this is tool tip, all right, and Ft therefore becomes root over Ff square plus Fr square, and this is in the horizontal plane. In the vertical plane we have the Fc and the resultant force R, therefore, this will become Fc square plus Ft square, is not it? This is the thrust force, and this is the resultant force, okay. Fr is the radial force, this is the radial force, this is the feed force, and this is the cutting force. Fc is the cutting force component, all right. So, this is what exactly shown here. So, Ft is the resultant force of the Ff and the Fr, okay, feed force and the radial force. So, therefore, 2 basic forces are there, Ft and Fc, so that the resultant force can be found out from the Fc square and the Ft square root over, all right. Now, when actually we measure the cutting forces on the machine tool, I will discuss it with you a little bit with the help of the dynamometer, that the measurement is made with the help of a dynamometer, and that dynamometer can measure the forces in turning, forces in drilling, forces in milling, and the forces in grinding, okay. So, particularly in case of the turning that we are discussing, the dynamometer will measure basically Fc and Ft. So, you have to determine the FF and the FR in case it is required analytically, in the sense that you know that this is the formula, okay, FF square plus FR square, this is the formula, and so on. Okay. All right. Now, these are the forces in the machining that is shown here, okay, as I have shown that. Now, here what is shown, what is given here is little more than what I have discussed here. Let us see what is in here. If we assume that the chip being a rigid body and it is moving, let us say at a constant velocity over the rake face of the tool with the VCH, this being the cutting velocity VC, all right. Then the resultant of the forces acting on the chip from the tool side through the rake face of the tool and acting from the workpiece through the shear plane of the process should be equal to 0. Once again I will explain it to you, that look at this figure. If we assume that this chip is a rigid body, okay, homogeneous body, and this is moving along the rake face of the tool with a constant velocity VCH. So, velocity can be constant if the resultant forces acting on the chip from here and from here will be the same, meaning the sum of these resultant forces is 0. So, let us say the resultant force coming to the chip from the tool through the rake face is R, and the resultant force coming from the workpiece, this is the reaction, all right. So, this is coming from the workpiece to the chip, this is the R prime. So, R and R prime, they have to be equal, opposite and collinear. Okay. So, their sum is 0 because they are equal, opposite and collinear, all right. Then only the chip being a rigid body can move along the rake face of the tool with a constant velocity VCH. Okay. Now, let us say this R, that is the resultant force, this we resolved into two components. One component will be along the rake face of the tool and another component will be the perpendicular to the rake face of the tool. Okay. So, this is the F, this is the N. Now, the N, since it is through the tool, so this is the normal force, and because of the normal force there will be a friction force F, all right. So, once again this resultant force coming to the chip from the tool through the rake face resolved into two components, friction force and the normal force. So, the normal force is the force which is which we are giving through the tool to the workpiece for cutting process, all right, and because of that normal force the friction force is created. So, therefore, between the N and the resultant force the angle will be called as the friction angle. Okay. In many places it is shown as the as this lambda, we are actually showing is as a beta, does not matter. So, similarly the resultant force acting on the chip from the workpiece through the shear plane, okay, R prime, that we can resolve into two components. This is one component is along the shear plane and another component along the perpendicular to the shear plane. Okay. Here there are two more things, one is the rake angle shown here, and this is the angle, I have already shown it to you that this is the angle between the rake, between the shear plane and the direction of the cutting velocity vector. So, this line is parallel to the cutting velocity vector and this angle is the shear plane angle, shear plane angle. In fact, it is written here. Once again the nomenclature, this is the friction force, okay, between the tool and the chip, N is the normal force, this is the friction angle we are taking as beta, Fs is the shear force. Okay. So, this R prime we are resolving into two components, Fs which is parallel to the shear plane, which is the shear force. Since it is parallel to the shear plane, and perpendicular to the shear plane is the Fn, normal force to shear. Cutting force is Fc and Ft, here it is shown. Now, to go to that, before that let me explain it to you that because of the change in the shear plane angle and the because of the alpha, okay, let us say when the shear plane angle is changing or the alpha is changing, in that case the resultant forces actually will change. Okay, you can understand that. Let me show it to you that if the alpha is different, that means if the inclination of the tool is different, then the direction of the F will be different and the direction of the N R will be different. Similarly, as the phi is changing, that means the inclination of the shear plane will be changing. All right. In that case, the inclination of the Fs will be, since it is parallel to the shear plane, so it will change the direction and so on. So, the r prime direction will change, meaning that with the change in the alpha or phi, the directions of r or r prime are not unique, do not remain the same. Therefore, the resultant force r prime, let us say, we will take this r prime we will write as an r 2 prime, let us say. So, this resultant force which is acting on the chip, again this can be further resolved into two more components. In fact, here only you can show that the same r prime we can actually resolve into two more components. One component will be parallel to the Vc and another component will be perpendicular to the Vc. So, this is called the cutting force, this is called the Ft, because cutting force, because this is parallel to the Vc. So, therefore, this force will be responsible for the power consumption, because Fc and the Vc product is the power, all right, and Ft perpendicular to Fc will be always the thrust force. So, therefore, now what we have is that we have 6 components, all right, 2 of the two components by resolving the r and 4 components by resolving the r prime, that is the F and the N in the rake face of the tool, that is along the rake face and perpendicular to the rake face. Fs and Fn will be on the, this is because of the shear plane, along the shear plane and perpendicular to shear plane, and Fc, Ft, these are the cutting force and the thrust components, thrust force component. So, once again that Fc and Ft we have taken because as you change the phi or the alpha, mind it, the direction of the Fc and Ft will not be changed. Okay, that is another reason that we have to take that Fc and Ft components, because the direction of the Fc and Ft component will not be changed with the change in the phi and the alpha, like in case of the r or r prime. Okay, meaning that Fs, Fn, F and N, these directions will be changed as we change the alpha and the phi, but Fc and Ft directions will remain constant, it will not change with the change in the phi or the alpha. Now, these angles, that is the alpha, phi and the lambda or beta, there is a friction angle, can be correlated with the components of the forces F, N, Fs, Fn, Fc and Ft, all right, together. Now, as you know that this relationship has been done for the first time by the Merchant and Ernst in 1944, and therefore, this is still being used as a valuable analysis or a valuable model, okay, showing the insight of the mechanics of metal cutting. So, therefore, this is called the model for the mechanics of metal cutting, which will give you the insight of the mechanics. However, this is done by them, if you see here, with the following assumptions. There are about 8 assumptions, and the assumptions are that tool tip is sharp and the chip makes contact only with the rake face of the tool. Tool does not have the round shape, nose radius. The cutting edge is perpendicular to the cutting velocity, You understand, we have said that in case of the orthogonal cutting, the cutting edge is perpendicular to the cutting velocity. The deformation is two dimensional, that is no side spread. Okay. Two dimensional means again the cutting edge is absolutely straight and it is perpendicular to the cutting velocity. So, if the cutting edge is perpendicular to the cutting velocity, deformation has to be two dimensional, that is no side spread. Note side spread of the chip, the chip will be flowing exactly perpendicular to the cutting edge and it will not be inclined to any side of the normal to the cutting edge. The deformation takes place in a very thin zone. So, this is always we are indicating by a line, all right, and we are saying that this is the shear plane angle, all right, shear plane angle, and this is the shear plane along which the plastic deformation occurs. But as a matter of fact, when actual cutting process takes place, the shear deformation takes place not along a plane, not in a plane, but in a zone. That means the this is actually a zone, not really a plane. Okay, it happens somewhere, sometimes like this, somewhere like this. But we are assuming that this is a plane for the simplicity of the analysis. So, all these assumptions, by the way, these assumptions are made by Marchant and Ernst to simplify the analysis. You understand that? Okay, because none of these assumptions can be valid in the actual process, actual machining process. Let us see, the tool is sharp. Tool does not remain sharp as soon as it comes in contact with the workpiece, for that matter. Okay. Cutting edge is perpendicular to the cutting velocity, does not remain true in case of oblique cutting. So, therefore, although this is simplified and this model is given for orthogonal cutting, where tool is exactly perpendicular to the cutting velocity vector, nevertheless with this analysis we first started understanding the mechanics of metal cutting. Okay. Therefore, even these days this model is used in practice. Now, the next assumption is the continuous chip without the built up edge. It cannot have the built up edge, because in that case this analysis will not be valid, it cannot be analyzed. Workpiece material is rigid and perfectly plastic. If the workpiece material is not rigid, then we cannot assume that the R and R prime are the equal, opposite and collinear. Okay. If it is homogeneous and if it is rigid and perfectly plastic, then only it can move along a constant VCH when the R and R prime are equal, opposite and collinear. So, this is another assumption. Next assumption is the coefficient of friction is constant along the chip tool contact length. This is the chip tool contact length, and along this length the coefficient of friction, this is the F by N. Okay, we will come to that. F by N is this, we are talking about friction force and the normal force, this is mu. Okay. And the tan of the lambda or beta, this is equal to F by N. So, this coefficient of friction is constant along the chip tool contact length. Next assumption is the resultant force on the chip R prime, this one, applied at the shear plane here is equal, opposite and collinear to the resultant force R applied to the chip at the chip tool interface. This is the chip tool interface. So, this R and this R prime, I have already told it to you that this is the equal, opposite and collinear. Now, if we draw the circle and if we draw the circle with a diameter of R prime, okay, R or R prime, they are the same, then draw the circle with this diameter. In that case, the tips of all these components will be lying on the periphery of this circle, because all these components Fs, Fn, Fc, Ft, F and N, these components are the resultant components of the one and the same resultant force R or R prime. Okay. Therefore, all the tips will be lying at the periphery, on the periphery of the circle. And as you know that this circle is called the Marchant's circle diagram, because this was invented as I said way back in 1944, okay, and this is for the mechanics of metal cutting. So, in this diagram, okay, this is the tool tip, okay, this is the tool tip. So, therefore, if we draw the line which represents the perpendicular to the cutting velocity, then between this line and the F, because F is parallel to rake plane or rake face, right. This line is normal to cutting velocity vector. So, the line between the rake face and a line perpendicular to the cutting velocity vector is the rake angle. So, therefore, this angle makes this angle is the rake angle. Okay. Now, then we said the angle between the normal force and the resultant force, all right, that would be in the rake here, as we said that this is the friction angle, all right. Here it is shown as the beta. So, this beta will be here. So, therefore, perpendicular to this line, all right, and perpendicular to this line is anyway n. These two lines also will make the angle which is the same as in here, which is rake angle. Okay. Now, the angle between the line which is parallel to the VC, this is parallel to VC because this is perpendicular to VC, all right, and this Fs is parallel to the shear plane because it acts parallel to shear plane, So, therefore, between the shear plane and the cutting velocity vector, this is the angle which is the shear plane angle, okay. And if this is the shear plane angle, then you can find out this being alpha, this will be the friction angle minus the alpha, okay, because this angle is 90 degree, all right, this angle is 90 minus alpha and so on. This angle you will be knowing as 180 minus 90 minus beta, all right, and so on. So, you will find out that this angle is actually equal to the friction angle minus the rake angle. So, these angles we have already determined. Now, let us see that how we can correlate these. Now, let us say the Fs. Fs from this triangle, all right, Fs is equal to this r prime into cos of this angle, and cos of this angle is phi plus lambda or phi plus beta minus alpha. Okay, this is what it is written here. Similarly, the Fn which is perpendicular to Fs will be r prime sine of this. So, if this is cos, this will be sine because they are perpendicular to each other, you know, Fs and Fn. Okay. Now, the Fc similarly, this will be r prime and the cos of this beta minus alpha. Okay. Now, this angle we have seen that this is the beta minus alpha, and therefore, Fc will be cos of this angle and the r prime, and Ft perpendicular to this will be r prime sine of this beta minus alpha. Then the f and n remaining. So, f here, this will be r prime and the cos of this angle. So, since it is 90 minus beta, okay. So, therefore, this will be f is equal to r or r prime, which is sine of the beta or the cos of 90 minus beta. Similarly, perpendicular to that is n, that is the normal force. This will be, if it is sine beta, so it will be cos beta because it will be r sine of 90 minus beta. So, r cos beta. So, these are the 6 equations that we can find out which will correlate the force components: shear force, normal to shear force, cutting force, thrust force, friction force and the normal force with the angles. 3 angles particularly, one is the shear plane angle, one is the friction angle and another is the rake angle, all right. So, from here you can actually find out that suppose you take from here R, okay. R is equal to Fs divided by this cos of phi plus beta minus alpha, all right. And from here you can find out that R is equal to Fc divided by cos of this. This is what we have written here. From here we can find out the value of the Fc, okay. This is the Fs and the cos of this divided by cos of phi plus beta minus alpha, all right. Now, Fc actually as I said that when you measure the forces using the dynamometer, you normally measure two components, okay, Fc and the Ft. So, therefore, as a matter of fact you cannot really measure and say that we have measured shear force, or we have measured perpendicular to shear force, or we have measured friction force. These forces can be calculated analytically from the measurement that you have for the Fc and the Ft. Okay. Therefore, in this slide whatever way we have expressed that Fs, Fn, F and N, this can be translated through the Fc. Of course, you understand that if you open it up, so this will be cos of this, cos of sin, cos this cos alpha, okay, plus sin of the sin alpha, and R of sin beta minus alpha is Ft. This value you can put in here, and finally what you can get is that Fs, which is this, can be also expressed through the Fc and the Ft in terms of Fc cos phi minus Ft sin phi. This is simple, you can find out, as I said that you open it up and then put the value of the Fc here as the cos R cos beta minus alpha. You will see that there will be a component of R cos beta minus alpha. In that sense, in that case you have to open it like cos phi cos beta minus alpha, okay, minus sin phi sin beta minus alpha into R, the entire thing. Then you put the value of the Fc, okay, put the value of the Ft, and you will get this. So, similarly for the Fn, normal to thrust force, it will actually have the Fc sin phi plus Ft cos phi. So, Fs and Fn we can this way we can convert through the Fc and Ft. Similarly, F and N, which is R sin beta and R cos beta, we can also express through the Fc and Ft. This is because sin of beta you can find out that this is beta minus alpha plus alpha, okay. This is sin, this is the same thing. Then you open it up and then you can find, you can put the value of this and this here, and you can find out this thing, okay. So, finally, you can get it that F is equal to Fc sin alpha and the Ft cos alpha. Similarly, the normal component will be opposite to that, that is Fc cos alpha minus Ft sin alpha. The rest of the material related to this I will continue discussing in the next session of discussion. Thank you for your attention.